Hi, this is Muhammad Iftikhar. I am explaining here my code I have did for my research project, MSc research project. So here I have imported unnecessary libraries which I am using for my code. So here is I have loaded the dataset, MNIST dataset. It's an image dataset. Handwritten numeric dataset. So I have imported this dataset to validate my neural network, not for specifically to classify the images. It's just for validation. And I have normalized the dataset into between 0 and 1, and I have stored the input and output in the variable x and y. So I have reshaped the encoded dataset and output dataset and store into the variable y1 heart. I have splitted the dataset into training and testing. 80% of dataset into training and 20% it into test. So here is the algorithm, neural network algorithm we have coded. So we have created a class name called fractional neural network which performs all the which perform fractional order algorithm. So let me explain before this. So the function dense, it takes number of layers with the number of neurons and store into list in the form of dictionaries. So let's start. So I have created I have initialized the input size 784 because of the matrix size, 28 into 20 the image resolution, and the output size is 10 because of it's storing the value from 0 to 9 digits. So I have created an object named called FNN for the class fractional neural network and giving the input size and the fraction power. So the power, what power exactly is? The main thing in the algorithm is the power. Because in the normal classical algorithm the power is always 1, but here what we have did it just we have tuned the power into the fractional value. This is only the main core and main thing in the algorithm, the innovation of the algorithm. So the dense I just explained. So I have created two dense layer, two hidden layer, and one output layer. So dense stored the layers as I have already done. So in total 3 layers, and one is the input layer. So we have called a train function for the object this, and it taking the training store variables x train and y trains with the epoch 10. Let's see what it's do. So as we have saw below that it's taking x and input and output with the epochs. So for each epoch it is calculating, it is going from the beginning of the input value to the end of the input value, like the length of the input for each epoch. Let's see here. So as I told, it's initialing from beginning to the end. So it taking input and output of each row and giving to the forward bias and backward bias, and calculating the epoch loss for the each of the for each iteration. So let's see what forward and backward bias doing. So as we saw, forward bias taking the input values and storing it into a list, and we have z values, which is nothing but the which gonna store the activation like after applying the sigmoid and multiplication of the input values. Let's see here. So Here what we are doing, we are just forward biasing the input values with the initialized weights. We have initialized the weight with zero, number of zeros, and with the bias number of zeros. We are just forwarding that input values by each layers as of the classical algorithm, same as Castle. But the thing in the backward pass, what we have changed, we have applied frag power to the error and the input values. So this is only the innovation of the algorithm, and the remains are all same as the classical algorithm. So what the frag power is doing here, let's see. Frag power is a method we have created here. Here is it is. So frag power, applying the to the value power to the value, but it's keeping the sign remains same and absoluting the value, then it's powering the value, so that the sign of the value should be remain same, and just it's applying the power to the value. That's all it is. Here is the sigmoid function and the derivative of the sigmoid function which we are using during the training process. Here we are using sigmoid derivatives and derivatives according to the formula. It's a simple code. I have coded for the formula, but the change, the innovation what we have did, we have applied. So frag power to the input values and all for each layers, and we are back propagating it here. We are back propagating with the same frag power activation functions, and to the whatever we are getting the weight values, we are deltas we are calling it, and up again we are back propagating the frag power to that, and we are storing the new updated weight and updated bias into a list. So that's all the code. And in terms of evaluation, I have already evaluated here that text test and white test evaluation. So in evaluation, we have got 90% of accuracy, 90%, approximately 95%. So what in evaluation is, we are predicting that what we have, the data set we have, 20% of data set of test data set, we are calling it and predicting it for the what predicting it by applying the stored weights we have got from the training, the store weights. So the store weights we are applying here, and we are and storing the value, the final value and the final list, and arg max is the variable, the Python method who gives the value which has have the highest probability. So that's all we are doing here, and here it is. Here is the accuracy we have calculated, which got 94.89%, and here is the prediction. So as what we have stored the weights, we are predicting with the same weights uh, to the test data set, and we are comparing that prediction with the actual y values. And here is the prediction. We have just selected the 10 images from the dataset to predict, and you can see the true is 5 and the prediction is 5, and it's all same for each of the image. So the prediction is 100% correct, you can see. So that's all the code it is. Here is the loss values how it has. Thank you so much.